Rolle's and mean value theorem, and this will complete all our new lessons for Chapter 3. So just very briefly, in Chapter 1 we studied the intermediate value theorem, and this is all in your textbook on page 77. But that said, if we had a continuous function, if we had some y value between the y values of our endpoints, then the function had to exist at every y value in between those. So it makes sense. On a continuous function, we talked about velocity, weight, height, speed. All right, they're continuous functions, so from start to stop, you would have to hit every single value in between. So now new, Rolle's theorem, and again, these figures can be found in your book on page 172. Let f be a continuous function on the closed interval and differentiable on the open interval. So in Chapter 1, we hadn't learned the derivative yet. So this condition didn't even exist yet, but now we have differentiability. If f of a equals f of b, then there's at least one value c in the interval such that f prime of c equals 0. So this condition should not be new. What would this like graphically? There'd be a horizontal tangent line at this value that we would find that we're calling c. And if we look at the graph, function is continuous and differentiable everywhere. Differentiable just meaning you can find a derivative. Then there exists some value where a horizontal tangent line would exist. Where does a horizontal tangent line exist? When the derivative equals 0. If you look at this figure, this function's continuous everywhere, but because it's a cusp at c, it's not differentiable. So Rolle's theorem would not apply, and therefore we couldn't make a conclusion from it. Notice f of a equals f of b. So the y values where you start and end have to be the same. Determine whether Rolle's theorem applies. If it does, find all values such that the derivative equals 0. If the theorem does not apply, explain why. 3 conditions for Rolle's theorem. Continuity, differentiability, and notice it's differentiable on the open interval. You can't find a derivative at an endpoint, so we wouldn't include them when we're talking about being able to find a derivative. And f of a has to equal f of b. Alright, a is the left hand of our interval, b is the right. So to show continuity and differentiability, I look at the domain of this function. It's all real numbers, therefore the function's continuous. When I take the derivative of the function, 4x cubed minus 4x, the domain of the derivative is all real numbers, therefore it's differentiable on the interval. And then my third condition, when I plug -2 into the function, 16 minus 2 times 4. This is correct, right? Yes. 16 minus 8. Oh, never mind. F of 2, 2 to the 4th, minus 2 times 2 squared. And we would get 16 minus 8. So all 3 conditions are satisfied. Continuity, differentiability, and then for these two, f of a equals f of b. Now when we start talking about theorems with the AP test, you do have to show that the conditions are satisfied, so I will be looking for that as well. Okay, now we can make our conclusion. The conclusion is that somewhere the derivative is equal to 0. So we already found the derivative to show differentiability. So I'm just going to replace x with c. Factoring out of 4c, I'm left with c squared minus 1. Setting each factor to 0. C is 0, and c equals plus or minus 1. So all 3 of those values are in the interval from -2 to 2. So we would include all 3 as our answers. And what does this mean? If we plug these values back into the derivative, they would each give us a value of 0, which means graphically there's horizontal tangent lines. What do horizontal tangent lines represent? There would be turning points at x equals 0, -1, and 1 on the graph of the function. Everybody's favorite. Domain of the sine function, all real numbers, so it's continuous everywhere. The derivative of the sine function is cosine of x. The domain of the cosine function is all reals, so you can find a derivative everywhere. F of 0 is 0, and f of 2 pi is 0. All three conditions satisfied, so now we set the derivative equal to 0. Now you don't have to replace x with c, but that's what the textbook does. So where does the cosine equal 0? Between 0 and 2 pi, at pi over 2, and 3 pi over 2. So those would be our answers, and that's it. Okay, the domain of this function, all real numbers, because we can take the cube root of negatives, therefore it's a continuous function everywhere. When we go to find the derivative using the power rule, 1 over 3x to the 2/3. When we look at the domain of this function, x can't equal 0, because a direct substitution would put 0 in the denominator. Since 0 is in the interval given, Rolle's theorem does not apply. Explain why, because f prime of 0 does not exist. And you're done. You can't move on. There should be a comma. Okay, when we look at this, domain of this function, x can't equal 0. 0 is in the interval that's given. Rolle's theorem doesn't apply. And again, why does it not apply? F of 0 does not exist. And you're done. Okay, so mean value theorem. This is on page 174 in your text. Let f be a continuous function on the closed interval and differentiable on the open interval. So the same first two conditions as Rolle's theorem. Then there exists a number c in the interval such that f prime of c equals f of b minus f of a all over b minus a. Okay, f prime of c, what does this represent? The derivative at c. What does the derivative represent? The slope of the tangent line. So what this theorem tells us, notice for the mean value theorem, you don't need f of a to equal f of b. What that ensured was that the derivative was equal to some 0 somewhere on the interval. Look at this notation. This is just the slope. This is the slope of a line through the points a, f of a, and b, f of b. So what does this mean? Somewhere the tangent line is equal to the secant line through the endpoints of the interval. Okay, a and b are the interval that we're looking at on the given function. And hopefully you can see this figure. So here's c. C is an x value between our endpoints a and b. The tangent line that we would draw at c is parallel to the secant line through the endpoints. Well, that makes perfect sense, because what do we know about the relationships of parallel lines? That their slopes are equal. So what does this tell us? The tangent line is your instantaneous rate of change. So when these conditions are met, continuous and differentiable function on a closed interval, somewhere the instantaneous rate of change, the derivative, is going to equal the average rate of change. And the average rate of change came from the slope. So determine whether the theorem applies. If it does, use the conclusion. Find where the derivative is equal to the slope of the secant line. If the theorem does not apply, explain why. Alright, so continuity and differentiability. When I look at the domain of this function, x can equal 0. That's not in the interval from 1 to 4 though, so it is continuous on the interval. F prime of x is 4x to the negative 2, 4 over x squared. Same domain restriction, but again, 0 is not in the interval, so it is differentiable in the interval. And they're the only two conditions you have to show. Now let's make the conclusion. So somewhere the derivative equals the slope of the secant line connecting the endpoints. So perhaps that is a little bit more side work. A is 1, B is 4. So find the slope of the line connecting those points. F of 4, 4 divided by 4 is 1. 5 minus 1 gives me 4. When x equals 1, 5 minus 4 is 1. This one comes out nice and easy. So now the conclusion says set the derivative equal to the slope of the secant line, excuse me. So Rolle's theorem, f prime of c equals 0. Mean value theorem, this number is going to change. So set the derivative equal to whatever slope we found. C equals plus or minus 2, but in the given interval, 2 would be the only value that we're looking for. The domain of this function, absolute value of x minus 1, is all real numbers, therefore it's continuous, and I did not give you the interval here. This is from negative 2 to 2. The derivative of this, however, we can look at the derivative, or we've looked at this enough. The derivative is not going to exist at the sharp turn. Where does the sharp turn occur? The sharp turn occurs at whatever makes inside the absolute value function equal to 0. So the mean value theorem does not apply. Again, how come? Because the derivative at 1, which is in the interval, does not exist. Okay, domain of this function, x minus 1 has to be greater than or equal to 0. X has to be bigger than or equal to 1. So it is continuous on the closed interval. We would include the endpoint. When we find the derivative, 1/2 x minus 1 to the negative 1/2 power. What's the domain of this function? Now we need all values of x bigger than 1. And the differentiability is on the open interval from 1 to 3. So it is differentiable there. So we can proceed. So the slope of the line connecting the endpoints. 3 minus 1 is 2. Square root of 2 minus 1 all over 2. I know you guys hate to see numbers like this. But now we set the derivative equal to the slope. So that's the conclusion. Okay, cross multiply. Okay, this is awful. So let's go back here. If we square both sides, it's still going to leave okay. We're going to run out of time here. So for your homework, solve for C. Find the value of C in the interval from 1 to 3 that makes this statement true.